Hi. So this video is going to go over how to find the Fourier transform of a Dirac-Delta function. What I have currently written is the equation for the Fourier transform, where we're going to integrate a time series, some function of time, and integrate that when multiplied by this complex exponential e to the minus j omega t. And we'll integrate with respect to time, and that will ultimately give us a function of frequency. Conceptually, what we're looking for is the presence of certain frequencies in our time series signal. And I'll go more in depth about that in another video. But for this video, I just want to look at the Fourier transform of the Dirac-Delta function. And just as a quick review of the Dirac-Delta function, the Dirac-Delta function is an infinite spike across zero time. And it can be located at some position. So usually we write this as delta of t. This is centered at the origin. So in my graph on the right here, I got a delta t, which is just going to be some spike at the center. And if I were to do some sort of transformation, I shift it around, I just need to change the input to reflect that shift. So if I do delta of t minus a, this is a rightward shift by a, whatever that amount is. And that's what I'm showing here in red. So the green one is just delta of t. The red one is delta of t minus a. That x-axis is time for this graph. Some interesting things about the Dirac-Delta function, if I were to integrate it, just the Dirac-Delta function itself, an infinite spike across zero time, this is a mathematical concept. We're going to say that the integral across that is equal to 1. This is the first important thing that we need to understand. An additional important thing about the Dirac-Delta function is that if I were to integrate the Dirac-Delta function, and I'll put it in the general case where it's a shifted one, and if I multiply that by any other function and integrate with respect to time, I end up getting the function evaluated at the location of the Dirac-Delta. Those are the two identities we need to do the Fourier transform of the Dirac-Delta. So now the question is, find x of omega for x of t is equal to the Dirac-Delta function. That's what we need to find. So we know, I already wrote the equation, I'll write it again. The Fourier transform of a function is going to be x of t, e to the minus j omega t dt. And in this example, I'm going to say that x of t is delta of t. That is the Dirac-Delta function. And based on this identity up here, if this function right here is my f of t, then this is delta of t minus a, where a in this example is 0. T minus 0 is what we have. So in this example, a is equal to 0. This whole expression is going to be equal to f of a, f of 0. So it's going to be e to the minus j omega 0, which is 1. Now, there might be some discrepancies if you were to Google what the Fourier transform is of the Dirac-Delta function. You might end up with a value of 2 pi thrown around in there. For our purposes, I'm going to write this down. For our purposes, We just care about where the content is. We're going to ignore the magnitude, theoretically, only focusing on where or what frequencies are present. So I basically just showed that x of omega is equal to 1. So if I were to plot this in the frequency domain, let's say that this is omega, I'll say that this is the magnitude of x of omega. This basically says that no matter what omega we plug in, we end up with a straight line that is at 1. This tells us that all frequencies make up the Dirac-Delta function. And if you were to go find some sort of spectrum analyzer online, and if you were to clap your hands, that would be similar to an impulse, kind of like a Dirac-Delta, not exactly because it's not going to be an infinite amount over 0 time, but we can model it similar to that. And what you would see in your spectrum analyzer in the frequency domain is all your frequencies would jump up because of the fact that that signal is composed of all frequencies. So basically, at omega is equal to 2, is that there? Well, it has a magnitude of 1 at that position. If I go to omega equals 1 million, well, it's there. Now, another important thing about this is let's go ahead and do what's called the inverse Fourier transform. And reminder that the inverse goes from omega to time, from frequency to time. So if we were given x of omega, we can find out what caused or what creates that x of omega. What is the time function? And by definition, and again, I'm ignoring amplitudes here. We have to keep that in mind. I don't want to be confused by that. This is just strictly conceptually about frequencies because there is a factor of 1 over 2 pi thrown around here, but I'm leaving it off specifically to focus on where peaks are, where is frequency content, not how much of it, just rather where they are. The inverse Fourier transform for our purposes is going to be the integral of x of omega now, e to the j omega t dt. Oh, sorry, d omega. If we are going to be going from frequency to time, we have to integrate with respect to omega, because once we do that integral, we would, in a normal case, just plug in the bounds for omega. So all of our omegas are replaced by numbers. They go away. We will end up with a function that is not dependent on omega. The only thing it's dependent on is t in that situation. And we can see the same thing true as here. When we're going from some function that's dependent on t, we're integrating with respect to t, that will give us strictly a function of omega. That's the Fourier transform, where we're going from time to frequency. The inverse is the opposite. We're going from frequency to time. So let's just see if we can work something out here. We know that the Fourier transform, and I'll write it like this, the Fourier transform of the Dirac-Delta function, we know that that is equal to 1. So if I were to plug 1 in for x of omega, what will I get for x of t? Because we should get the Dirac-Delta function. to the j omega t. I did it again. The omega, sorry. It's very common to write dt. The omega. And this is not a function that converges. This is a function that if you plugged in infinity into it after plugging in the bounds, you would blow up. But what's interesting is that we know this has to equal the Dirac-Delta function, because that's how we get the 1 in the first place. That 1 is the Fourier transform. So if I do the inverse of it, I better get the Dirac-Delta function. So what that means is the Dirac-Delta function is equivalent to the integral of e to the j omega t d omega. Is what that is telling us. And let's just think about this for a second. Does it matter which integration variable I go between? Here's an omega, I get delta of t. Is there anything stopping me from saying delta of omega is equal to the integral from negative infinity to infinity of e to the j omega t dt? Because if you look now, I have a function that I'm integrating with respect to time, and my output is a function of omega. These are both valid expressions. This confuses people because we think about the Dirac-Delta as being this impulse that occurs at some period of time. But from a mathematical perspective, we can still plot it in the frequency domain. So if I were to integrate e to the j omega t with respect to time, I would get delta of omega. I'm just going to try to draw a plot to represent this. So let's say that I give you, this is the time domain. This is time. This is delta of t. If I do the Fourier transform on it, I would get this constant value of 1 throughout the whole thing, or this amplitude, whatever it is, that is valid for all frequencies. So this is frequency in this case. Now, if I were to say instead, let's say that instead of having delta of t in the time domain, let's assume we have a constant value of 1. If we were to go to the frequency domain, we would see a Dirac-Delta function present at that location. So we would see the Dirac-Delta function would be delta of omega now, frequency. Which should make sense. This is just a mean value that doesn't oscillate. It's going to have a peak at the origin. That's 0 hertz. There's no time varying component, therefore the frequency is 0. So mathematically speaking, if I do the Fourier transform of the delta function, the Dirac-Delta function, I would get this constant amplitude. I'm trying to make it horizontal, that's better. If I were to take the Fourier transform of a constant line, a straight line, it would give me the Dirac-Delta function. And that's essentially what this is saying. In this example, my function, my x of t is equal to 1. In this example, my x of omega is equal to 1. This was the original Fourier transform, this one that we did before. This is what we just learned from our second derivation going backwards. They end up being mirrored pairs, essentially. And this fact here, these two equations will be very useful. I'm going to do this in a separate video when we find the Fourier transform of, let's say, a cosine wave or a sine wave, something that is periodic. And we'll talk more about that in the next video. If you have questions, please let me know. Okay, thank you.